एक सेकंड, क्या बोल रहे हो? हाँ, एक मिनट। स्क्रीन स्टार्ट कर दिया। ओके। आई थिंक या दिस शुड बी गुड नाउ। हाँ, बोलो वो जरा। यहाँ क्या मरी? या आई थिंक नाउ इट शुड बी गुड। हाँ, अब ऑडिबल है। ओके, ऑल गुड। और यहाँ पे एक होता है ना, बोर्ड गूगल मीट का। हाँ हाँ। नहीं, मैं थोड़ा वो ढूंढ रहा था, कुछ लिखने का भी कंटेंट होगा ना। अब डायरेक्ट मेरे पास कुछ स्लाइड्स तो बनी नहीं हुई। लिखना पड़ेगा मुझे तो लिखने के लिए व्हाइट बोर्ड वगैरह अभी। प्रेजेंट तो ये होगा ना शेयर, आई थिंक। प्रेजेंट तो ठीक है, मुझे व्हाइट बोर्ड चाहिए ना, पहले मैं वो ढूंढ रहा था। अ, अभी क्या करता है, रैंडम टैप प्रेजेंट करता है। ये तो आ रहा है ना। और मेरी आवाज पता नहीं क्यों ऐसे 10 सेकंड बाद एको के वापस आई है। व्हाइट बोर्ड ढूंढना है। और एक और 2 और मिनट। 7-10 पर, 5-10 पर। हाँ जी। बाकी कैसे प्रेजेंट करते हैं, थोड़ा आइडिया दो। किस चीज का? नहीं, प्रेजेंट कर सकता हूँ मैं। आई एम सेइंग कि टू द नेक्स्ट स्लाइड, और या कहाँ पे प्लेटफॉर्म पे लिखना हो मुझे कुछ, तो कहाँ लिख। मुझे कहीं कुछ लिखना हो माउस से, तो कहाँ लिखूँ मुझे? जूम पर। Okay. मतलब जहां तक मुझे याद है इसका गूगल मीट का व्हाइट बोर्ड हुआ करता था, मिल नहीं रहा। प्रेजेंट में व्हाइट बोर्ड का एक ऑप्शन आता था, वो अभी दिख नहीं रहा है कहीं, इसलिए आइडिया हो गया। हाँ, सही है। इसका सेकंड है। एक मिनट और। स्क्रिबल यूज कैसे करना? स्क्रिबल डॉट आईओ बोल रहा है, स्क्रिबल एक्सटेंशन बोल रहा है। ऐड करने में भी बहुत मुश्किल। ओके, ऐड कर लिया। आई थिंक एक ऑनलाइन प्लेटफॉर्म मिल रहा है, आई थिंक। और एक ऑनलाइन व्हाइट बोर्ड का एक वो मिल गया, फ्री आए दे गया। क्या है? सो दिख रहा है ना? क्या? ऑलरेडी है सब कुछ, रेस्टोरेंट। हेलो, स्टार्ट कर दूं? Yeah, so we'll be looking into some of the topics of number theory. Uh, So the first one we would be looking at is linear series. Yeah. Uh, so generally, the normal series for calculating things is of the order of in log n or in log n generally. So linear series is a great technique for having yeah. So linear series is a great technique for calculating every like the number of times or any multiplicative function till for all numbers from 1 to n such that like in order of an order. So what we do in linear series is that uh, yeah. So what we do is that for calculating the function that we want to calculate at the time. So multiplicative function. So the definition of multiplicative functions is that f of a into b uh, equals f a into such that and we are perfect. Yeah. Uh, yeah. So how does solve? Yeah. So how do we do this? Is that for every number we go through its prime factorization. For example, there is a number with prime factorization with something like this. Okay, with a 3.5. So first we calculate the function at 5. So the the calculation chain for this will go like first we will know f of 5. From that we will calculate f of 5 into 3, and from that we will calculate f of 5 into 3, and so on. So so how do we do this? So a common example for this kind of function is the Euclidean function, which denotes the this denotes the this denotes, uh, 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 yeah. So for calculating this, uh, the linear shape was like we calculate for every number we calculate this function by first calculating the lowest prime factor of every number, and then through the lowest prime factor, we first calculate f of n by its lowest prime factor, and from that we calculate f of n. So for the Euler-Toscan function, the code looks something like this. So first, what we do is we declare three vectors. So let's uh, and we just create here, lowest prime factor times size and plus one size of primes is unknown, and uh, the function, let's say, and so for every multiplicator function, you know that f of one is one. So that, and then we uh, and uh, now if the lowest prime factor of I is not assigned, which means I is assigned. Uh, oh, yeah, just without just wanted to confirm that. I think these portion will be available from online, so I think I can write it. Okay, I'll, I'll take it from you. Yeah. 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 Yeah, वही क्या टेम्पलेट भेज दिया ओके ओके या वही प्रेजेंट कर देता हूँ ना स्क्रीन पे ठीक है ना ओके या फिर ठीक है पेस्ट में ऐसा तो any other person yeah yeah so in this we have just created a limit it's the lowest prime factor LP and PR. So the locus from 2 to n, if the lowest prime factor is 0, which means I is prime, so we push back I in the primes list. Now we iterate over the primes list and we just assign the lowest prime factor of I into prime of j as PR of j. And uh, this condition here it is just written below, or you can just include it that whenever PR of j is greater than equal to LP of I. We just break because now we don't know what the lowest point of that number would be. Yeah. So coming back, this It's coming. Okay. Yeah. So yeah, that was a part of linear sieve. Now to include how to calculate any multiplicative function in this. For example, of Euler-Tessent function, what we do is we will just assign it to I minus one here only in this portion of the or let me do it on MD, I think. Yeah, so for example, we want to calculate ETF. I'm going to declare it here, ETF of I is equals to I minus 1. And for this, we have a condition. I think. Yeah. So ETF of I into the of equal to I ETF PR into PR. So we know that for I also, the lowest prime factor is PR of J only. So we have included J minus 1 already. And else if we have equals ETF of I. So that concludes how to calculate Euler-Tessent. So in Euler-Tessent function, I guess this condition is pretty easy. But generally, what we do is whenever we have to calculate some complex function, what we do is we keep this condition first, and uh, instead of just calculating here it for I, we calculate here for all powers of I, and then we don't go over the same time. I'll explain it in detail in uh, later, like after, and I'll come back. Yeah. So that's about it. Uh, yeah. Yeah. So the next topic I want to go on is about the extended Euclidean algorithm. Uh, I think most of people know the normal Euclidean algorithm for calculating CPC of like two numbers. The extended Euclidean algorithm is used for solving linear differential equations like of the formula x plus cy is equals to c, where given a comma b, a b and c, and we have to find some x. Some. So the solution for this is that this is only satisfiable when basically one of the uh, and now if we find a solution for let's say ax dash plus y dash is equals to a comma b. Then we can just multiply it by some factor. For example, if this would be a comma b divides c, then divide c is equals to this would be a comma b equals like dash. And now we know the original solution is x equals x dash equals y equals y. Yeah, so the only problem remains is to how to find this solution. The solution of a x dash plus b y dash equals to c d. So for that again the algorithm is pretty known. We do it with the help of it as well. Right, right. So we know our solution. The normal GCD function, for example, looks like this. So the normal GCD functions look something like this. But in extended Euclidean, we want to return their intent, like x comma y. So what we do is, so first if b is 0, then we know that a is the GCD of the numbers. So we can write a as a into 1 plus b into 0. So we would write first. Now else b is not 0. First we calculate the answer of the next step. Like first we say, oh, where, oh, yeah, and now we have the solution for b and a mod b, right? So for example, we know that g is I'm not in the GCD. And this is what we wanted to find, right? Uh, and what we have right now is b into x dash sum x dash. So we know x dash and y dash now. Because, yeah, plus a mod b into y. So we want to find this, and we have this. So what we do here is just uh, substitute mod b is equals to hmm, a minus a by b, like automatically execute. So now if we expand a mod b like this, what we would get is uh, g is equals to a divided plus x dash minus a by v into y. Yeah, just a by v wherever I'm writing it lower all lines. But yeah, so now what we do, we just return this one. Return. Uh, so y dash just denotes next plot second, and x dash is next plot. So we have to return y dash comma x dash minus this small first minus a by b. And that's so this extended Euclidean function gives the solution for this. Now we have these x dash and y dash, and now for calculating the original x and y, we just multiply it by c divided by g, and we can get a solution. This is quite useful in many cases. This is quite useful in many cases. Uh, yeah. So if like yeah, so the most uh, the an example where this might be useful is, of course, you could find many problems regarding this. One more use case in which this is commonly used is finding modular inverses. Like everyone knows that, uh, or like currently for modular inverses, what we use is just simply modular inverse is equals to past exponential a mod uh, like this works for primes. Uh, yeah, so this works for primes, but if mod is not prime, for example, so uh, by a extended Euclidean theorem, we I don't know, it was some extension of another theorem. So what it said was a power pi of I of n equals 1 mod n if uh, so using this we can find mod inverse a is simply cost of a pi of n minus 1 and mod n. So but in cases where phi of n is not easy to calculate, like phi of n takes, like for a single number, it takes order of Newton complexity to calculate. So let's say if n is pretty large and there are multiple test cases, it won't be feasible for to every time have n and to every time calculate phi of n. So how to find modular inverse is, so extended Euclidean algorithm makes it pretty simpler to find modular. Uh, my model. Extended Euclidean makes it pretty easier by just having what we can do is we can have pair of int uh, and, equals, let's say, expand the extended Euclidean of a and n. Now, what if a and n are co-prime? We are assuming that, of course, without that we can't find an inverse. So, of course, if a and n are co-prime, we know that temp is a pair of, let's say, x comma y, such that a into x plus uh, n into y is 1, because we know the GCD is 1. So temp just has a pair of that, and we can, if we take this whole thing modulo n, then we can say that a into x modulo n is equal to 1, which means x is the modulo n. So uh, the modular inverse is simply x. Now, if in the case x is negative, we can do it mod n and then plus n. That can be. So it's a use case of. There are many other too. It's one use case of extended Euclidean where you just simply have to find inverses, and you can't afford to calculate phi of n every time. Yeah. So this covers it. Oh, yeah. You want to say something like that? Oh, अभी क्या अभी भी खराब ही है. ओके वो थोड़ा पीछे हो गया था माइक. अच्छा. ओके बना. Oh, okay. Yeah. Better now? Okay. ठीक है मैंने हेडफोन क्या कर लेता हूँ मैं फिर. ओके. या वन थिंग मेरे साथ वो शेयर कर दोगे इसी चैट में ही यूट्यूब स्ट्रीम का लिंक भी. आई कांट सी एनी चैट और समथिंग. हाँ चैट पर डाल दो ये बोलो. थैंक यू फॉर दैट. Okay, I'll see. I will see the comments if there are anything. Huh? Oh, okay. Okay, I don't see any like doubts. Okay, we'll continue then. Yeah. So next topic is CRT. I thought of it, but like I think there are many blogs on it. You can learn it from there. The main thing I wanted to cover was mainly multiplicative function algebra. So I think I'll straight up jump into it. Okay, so yeah, I'll straight up jump into multiplicative functions. Yeah, so yeah. So, what are multiplicative functions is f of, yeah, I guess I've told it earlier, but still I'll tell it again. You know, f of a into b is just simply the product of f a and f b, uh, given receive t a comma b is equals to 1, right? So, uh, uh, yeah. So, in multiplicative functions, there is an important convolution known as Dirichlet convolution. What this says is that, let's say you have two functions, f of n and g of n. So x is f. I don't know how to draw the convolution sign on keyboard. I'll just use the multiplication operator. Dot, or I can use OIS. Yeah, small o, I guess. This is this. I'm using it as a sign. I hope I'll maybe use cross. No, oh, it's fine. F of g. We say this condition. It is and g. And what this means is that h is equals to h of n for any integer n is equals to sum over all divisors d such that d divides n. F of t multiplied by g of n by d. That's the definition of Dirichlet convolution. So it's quite useful. First, I'll just explain some of the basic functions that we have, and then we will go on to derive some new functions. Maybe you already know those. I'll derive them from here. Yeah. So the basic functions that we know are first the, of course, f of n is equals to n. I forgot what it was named anyway. And one is f of n equals 1. This is called the unit function. And one is f of n is equals to n equals to 1. This is called the identity function. This function is this is 1 at n equals to 1 and 0 otherwise. So yeah, why is it called the identity function? So in anything, identity is something that you like, for example, the additive identity in numbers is 0, the multiplicative identity in numbers is 1. Identity is something that you apply the operator with, but result still is unchanged. So if I apply convolute any function with the identity function, so let's say I have function g of n, I convolute it with identity function. The result will still remain g of n. Okay. I have done it now. Something like that. Right. So, basically, whenever you try to calculate this sigma, uh, the identity function, if that is 1, so it will return g of n and otherwise all 0. So, this eventually will converge to g only, right? And now there are some definitions like inverse of a function. With respect to Dirichlet convolution. Yeah, so if I try to uh, calculate the inverse of a function, so inverse of a function, let's say capital capital F and capital G are inverses of each other. That uh, capital F convoluted with capital G is identity, right? So that's how inverses are defined in group theory. Uh, so here also it's just a group of functions, and the operator here is the Dirichlet convolution. So now if we try to, let's say, find the inverse of unit function. Instead of trying to find first we'll see there is a theorem. I don't remember what is the name. So the theorem states that the Dirichlet convolution of two multiplicative functions is also multiplicative. You can prove this by just substituting, taking two independent numbers, let's say a comma b, and for each divisor d1 of a uh, and d2 of b, every divisor of a into b is of the form d1 into d2, and every occurs just once because of the coprimality of a and b. This can be proven easily. So, uh, this theorem is quite useful. Using this, we will now try to find the inverse of unity function. So basically, let's say using this theorem only, we say this that if f convolution g is h, for example, if any two of the three f, g, and h is multiplicative, then the third one is forced to be multiplicative. Any two f, f, g. Right. So if we try to find the inverse of unity function, so let's say this f, let's say f denotes unity function for this, and g is, let's say, the inverse of unity function, and h is identity. Now we know that unity function is multiplicative, like it's one everywhere. So of course, f of a into b is f a into f b always. Identity function is also multiplicative. You could check it on any co-prime pair a comma b. It will work because it's just one on one and else. Yeah. So now we know f is multiplicative, h is multiplicative, so g also has to be multiplicative. And for finding multiplicative functions, we just need to find them on towers of primes. And because of their multiplicative property, we can find it on any number. For example, if we have found it on a prime p, we know, let's say, f of p, and we know f of q also. We can just find f of p into q just by multiplying fp and fq. So for multiplicative functions, we just need to find them at the powers of primes, and that's all. We are done there. So we will try to find g only at powers of primes, and then because of its multiplicative property, it could be found everywhere. So let's try to find g at we, as we know, g is a multiplicative function, so g1 has to be 1. Now we will try to find it on a prime. So let's say g of p is some prime. So g of p is just equal to so we want to find g of p. So what we will do is we will just apply the definition of convolution. So we know that h of p, like h is the identity function here. So we know that h of p is 0 because it was 0 everywhere except 1. And we know h of 1 is 1. And we know f of 1 is 1 and f of p is also 1. And now what we want is, and we know the convolution relation also. So if we find h of p, we can write it as, so the divisors of p are just 1 and p. So h of p could be written as f of 1 into g of p plus f of p into g of 1. Right. So we know the value of g of 1, it's 1. Right. So we can just write it as 1 is equals to f1 is 1. So it's g of p plus, sorry, h of p is 0. My bad. And f of p is 1, g of 1 is also 1. So we can write this plus 1. And we can say g of p is equals to minus 1. So we know that whatever this inverse of unity function is, it's minus 1 at all primes. So now if we try to calculate it as at some prime square, so we will see again h of p square. This could be written as f of 1 into g of p square plus f of p into g of p plus f of p square into g of 1. So we know that f is 1 everywhere and h. Yeah, sorry about that. It was a network issue. Sorry about that. 1 second. Sorry about that. I hope it just loads. Ah, the castle we lost. My bad. What is it? Oh no, it's not. Hang on. Yeah. Oh, yeah. Here. So we know that h of p square is 0. Uh, and we can just I think my screen is visible now. Yeah, h of p square is 0 and f is 1 everywhere. So we can write it as g of p square plus g of p plus g of 1. Again, we know g of 1 is just 1 and g of p is minus 1. They already sum up to 0, so g of p square is 0. Right. And now whatever we try to compute, g of any further power is again 0, like g of pq, etc., and everything is 0. So if we try to calculate g at any number n, so it would go like, let's say if n is let's say p1 power x1 into p2 power x2 till pk power xk. Right. So now we can just say that g this would be equal to g of p1 power x1 into g of p2 power x2, as p1 power x1, p2 power x2, all of these would be co-prime only. Now we have found g on these. So if any of the powers is greater than 1, then we for sure know that g of n is 0. We can say that if n is not square free, we can say that g of n is 0. Now, if any of these xi is uh, not greater than 1, means each of these is equal to 1. So, uh, now, so just it's the case when n equals p1 into p2 till pk. Now, we know that g of pi is every prime is minus 1. So, for any n, uh, it's just uh, it would be just minus 1 power k mod 2, minus 1 power k or k mod 2. Yeah, so if we formally define g of n, this is has three cases. 0 if n is not square free, or actually two cases, and minus 1 power number of prime factors. Yeah, so this function that uh, is the inverse of unity function can be calculated via this, and g is called also called the Mobius function. So Mobius function, maybe some of you have heard, is nothing just but the inverse of unity function. So, this is the definition of Mobius function, and it's quite helpful to have Mobius functions such that I'll take an example. Uh, like you have given a function g such that g of n equals sum over all divisors f division of p. So, let's say and we have to find that. So how would we solve this? So I'll see there are any notes. Okay, I think no doubts till now. So if we have to find f, what will we do? So we know that given g is equals to f convolution unity, and to just find uh, f, we can just convolute g with Mobius. So convoluting both sides by Mobius, and yeah, the Dirichlet convolution is associative. So we can take care of this part first, and we know this is identity, and f convolute identity would be f only. So we know G convoluted Mobius is just f, and this can be calculated by a simple sieve. I say. Okay, uh, that was about Mobius. Also, there are some interesting properties about Euler-Gaussian function. Like, let's say phi is the Euler-Gaussian function, and f of f is a function such that fn equals n, then phi is nothing just but the convolution of f and Mobius. Again, the definition of phi is like that only. No, the number of co-prime numbers that you have, for that you would like to apply, I would say, like, for example, I would say that. So how many numbers are co-prime to n is phi, right? So to calculate this, we know that uh, uh, if we want to solve this problem, uh, how many numbers have GCD is equals to I with n less than equal to m, have GCD I with n in numbers. Uh, so this is just simply phi of, uh, I think, in given I divides n upwards. This is just simply phi n by I, because we divide both the numbers by I, and now we can say that their GCD is 1. So if we sum phi from overall divisors of n, that's just saying sum all the numbers which have GCD equal to I let's say some phi n by I over all I reading n. So basically we are saying is how many numbers are there such that they have GCD I. If we sum them all, those would be equal to n, right? Because every number will have some GCD with n, which is a factor of n. So with that, we claim that phi convoluted with unity is just f under this function. Yeah. So those were some properties about multiplicative functions. I think I've covered it enough. Without what I wanna ask is this, like, should I give a list of problems at the end or should I do it now? Okay, okay. So there is a blog on code forces that has some examples. I don't think I need to specifically do it. I think I'll just resolve it. Uh, क्या किसका अच्छा ये हाँ दिस वाज अ ब्लॉग ना एक्चुअली इट हैज सॉल्यूशंस आई डोंट थिंक मुझे उतना एक्सप्लेन करने की नीड है लाइक द एग्जांपल्स आर क्वाइट गुड ओनली so yeah, in this example number one, I think many of you can try this only. Maybe I'll put the link in start of YouTube only. So you could try this. Uh, uh, yeah, also, you share the resources in the end, right? Maybe leave this blog link in comments only, right? I'll see the YouTube. Uh, so, have any of you tried? Any ideas? I think the solution is given there only. हाँ मैं अगर मतलब किसी ने ट्राई किया है कमेंट्स में कुछ दिखेगा अनकंफर्टेबल बहुत है हाँ कुछ कह रहे हो ओके वही कर देता हूँ सोल्यूशन मैं क्या बताऊँ ऑलरेडी दिया ही हुआ है मैं रीड थ्रू ही कर देता हूँ फिर like should I write then yeah so it's asking the number of pairs such that जिनका GCD one equal to one है it's just calculating whether GCD ij equals one so by the definition of Mobius function, it is the inverse of unity. So if we sum the Mobius function, it sum the Mobius function over all divisors, it's simply the identity function, and it's just saying that we have to on GCD we have to just sum the identity function only on all common divisors. So if we sum the identity function on all common divisors, we would get our answer, and this is just simply doing that only. For each divisor, so it's a d divides g c I j, and now we can break this in d divides I and d divides j. And now I and j, we will just replace the sigma, take d over the left side, and this is simply just n by d, both sides. And the answer will be simply mu of d into n by d whole square. And this can be computed using, yeah, in order root n. But yeah, order and login, I guess in and login this can be easily computed right now. But yeah, for further, I guess we need to learn more advanced techniques. हाँ एक काफी है ना ठीक है ओ ओके ओके मतलब I don't know should I try some other topic या थोड़ा और एडवांस जाऊँ इसी का क्या और एडवांस आता हूँ फिर I go with- I guess there are many blogs on this but ठीक है I'll still go with it. Okay. Yeah. I don't know. Let me think where to start. Yes. So Min 25 sieve is something about like these all convolutions that I said. These are like good. I'll share some problems on these also. Min 25 sieve is Uh, Basically, let me start with the basic problem. How many prime numbers of this equals to n given n? So for this, the general techniques that you would know are sieve, that's n log n, and earlier I told in this lecture only linear sieve, that would be odd n, but this can be calculated like for the lesser complexity. So I think let me straight dive into it. So in sieve, let's go over. In normal sieve, what we do is we iterate over all primes and try to see if we can eliminate more numbers that are not prime. So basically, when we are iterating, so first we go on 2, then we go on 3, then we go on 5, till let's say we are at some p. So let's say I want to know that, uh, like, how many numbers did just this single iteration eliminate? Like 2 eliminated some numbers, 3 eliminated some numbers, 5 eliminated some numbers. So how many just the computation, how many just this P eliminate? So this is all the numbers that the loop of P will eliminate is are just numbers n such that LPF of n is P. LPF is the lowest prime factor. Yeah. So uh, we know that for an integer n, if we loop over it and like we loop over all prime numbers and we just eliminate all its multiples, that these are not prime. So how many extra numbers are eliminated are just the numbers which have the lowest prime factor that is equal to p. So instead of just brute forcing over there, we will try to have some kind of dp so that we can calculate these numbers efficiently. So let me define a dp. That's a dp of n comma I is such that how many numbers less than equal to n have LPF greater than I. Let's say. Yeah. So if uh, for sure, like we know that if we have DP of n, now at the end, just have to calculate the number of frames, right? Yeah. So or R prime, let's say. Let's say DP and I just denote that how many numbers less than equal to n are not exactly this. So basically, it's sorry, my bad. How many numbers are left to be candidates of prime after we run the till I? Like, uh, how many of the when we make a Boolean array like is prime and we run a sieve. So in the first loop of I, if uh, we are currently at some number, the dpn comma I denotes that how many trues are still left in the array after iterating till I. If if I is, now we will get some, have some cases. If I is prime, sorry, if I is not prime, let's say. Uh, yeah, and one more fact that we know is that we don't need to run I till n, instead root n works. So if I is not prime, we can just say dp of n comma I is just simply dp of n comma I plus 1. And the number we want to calculate primes till n, let's say, is just dp n comma root n, right? Because when we see out till root n, only primes are left, right? So if I is, let's say, not prime, then we can say dp n comma I is just simply dp n comma I plus 1. Sorry. Uh, we are defining a recursive function here. No, actually. Yeah, we have to find dp n comma root n. So this is do this. Yeah, yeah. I would say, yes, if we want to calculate for dpi, we can just say it is dp and I minus 1. Yeah. We know dp I comma 1 is n minus 1. Sorry, n comma 1. Because except for the number 1, we consider every other number to be prime, like from 2 to n. So dp n comma 1 is just n minus 1. Now, if I is not prime and we are trying to calculate dp n comma I, it's just dp n comma I minus 1. Now, if else, now how many numbers will get eliminated more? So we know that dp n comma I minus 1 has eliminated till I minus 1. And now we want to eliminate I. So now we have to calculate the number of numbers which have lowest prime factor as I, right? So we can say that those are not eliminated till I minus 1. And if we multiply I into them, then those are the candidates we are trying to eliminate. So this would be simply dp n by I, comma I minus 1. So till n by I, if we calculate how many numbers are sieved out till I minus 1 and we multiply I in each one of them, these are the numbers that will get eliminated, right? But some numbers would already be eliminated. That would be some form of I into, uh, let's say, some number is of the form I into k. We are trying to eliminate these kind of numbers, right? So if k has a smallest prime factor I, then we are good with it. We want to eliminate that, right? Because I into k will also, if k has a prime smallest prime factor greater than equal to I, then I into k has the smallest prime factor as I, and we want to eliminate these numbers only. But if k is less than I, then we know that uh, we want to eliminate. So if k is less than I, then we know that k should be a prime because those are the numbers we are considering. So we overcount the elimination of these. That's why we, from the subtraction, we first eliminate till these numbers. So this would be uh, primes till I have. or we could say dpi comma I. Right. So dp n by I minus 1, and then dp, what can I say? And how many numbers are of the form like I into k till n by I? Uh, Not exactly this. Primes till n by I that are less than equal to I. Primes till n by I which are less than I. So these are all the numbers that we don't want to eliminate, because multiplying I into them is always already eliminated, as they all have a smallest prime factor of less than I minus 1, right? So for this, mm, we create a DP, and we can implement this by map. Like if we try to implement this DP by map, at the first it seems like it's almost quadratic or n root n, but actually it's much less than that. And for calculating this can be also written as some DP. Yeah, dpn by I minus 1, I think. Will that be true? No. Uh, Let me write this as dp I minus 1, I minus 1. Let's go with that one. Yeah, anyways, so we would be dealing with, so we know that for, we would only calculate until I is not root n. So once I is root n, we just stop this process, because we know that further eliminating wouldn't help, because in sieve also we only run till root n, right? So instead of writing this, we can just say number of primes till I minus 1. So to calculate this dp, what we do is, the first step is linear sieve till root n. So first we apply linear sieve till order, till root n numbers. Calculate how many primes are there till, take a prefix from 1 till 0, prime and not. And then we know that till n how many primes are there. And just recursively implementing this DP, this gives us a complexity of order of n power 3 by 4. I'll explain how it is n power 3 by 4. So in this recursion, we can see that we only go on the terms that are on the left side number could be only of the form n by I, as sorry, uh, because we know that if I divided the by j for the sum j, this is n by I into j only. This is the property of floor. So we know that all the numbers on the left side of the DP, like the first number of the DP, is always of the form n by I, right? And the second number of the DP is just at max as root of the first number, right? So the number of states of this DP is simply sum I is equals to 1 to n, uh, sum over all numbers of the form n by I. Let's say this number is some j, and we have to sum simply root of j, because the second thing would be root only. This could go up to root j only, because after that all the numbers would be same. So replacing this, so for if I is till root n, like we divide this into two parts. If I is less than or equals to root n, we can just say it's n by I into root n by I. It's just sum I equals 1 to root n by I into root of n by I. So only root n by I multiplying. Sum over all these. If we replace this sigma by integration, it gives us a good approximation, which comes out to be n power 3 by 4. And for the other part, we know that if I is greater than root n, then we for sure know that j is less than root n. So summing up, sum j equals 1 to root n root of j. This is also bounded by n power 3 by 4. So both these sums are bounded by n power 3 by 4. So their addition will also be bounded by order n power 3 by 4. So the total complexity is bounded by order power 3 by 4. Yeah. So this is a pretty useful tool to calculate the number of primes less than equal to a number. In a similar fashion, like how we calculated this DP, we can have it for sum of primes also, or any function of prime, like sum of primes, number of primes. Mostly these two are sufficient only. And using this Min25C, actually we can solve a lot of problems. Like there is a problem on sports called Livesey and decay. Okay, not available right now. Uh, what do I do? The problem is not available. Should I provide it as a practice or give the solution? Vedant? हाँ नहीं नहीं बंद नहीं करना मैं पूछ रहा हूँ क्वेश्चन प्रोवाइड करूँ और ये क्वेश्चन का लिंक अभी इनएक्टिव दिखा रहा है क्वेश्चन जो प्रोवाइड करना था स्पॉज पे है उसका लिंक इनएक्टिव है अभी अच्छा ठीक है लो ये देखो ना सर्वेशन अवेलेबल दिखा रहा है हाँ ठीक है तो अभी फिर इतना ही बता पाऊंगा और ज्यादा बता नहीं पाऊंगा ब्लॉग शेयर कर दूंगा फिर प्रॉब्लम्स को वो लेके बताऊंगा मुझे ओके एज यू से लाइव होता तो बहुत बेटर रहता बट ठीक है नो इश्यूज yeah so next topic I decided was I'll skip these I think ये टाइम काफी हो ही चुका ऑलरेडी I'll mainly focus on Lucas theorem and इस प्रॉब्लम पे फोकस करके I'll just end the session right so let's go with Lucas theorem so if we want to calculate NCR what we given P is comparatively small and N and R are large. So how do you do that. Yeah. So how would we proceed in this calculating? So Lucas theorem directly states that first we convert n and p and r into base p. So let's say it is, and for example, they are candidates. Converting into base p is simply easier, as like we just don't have to do by p and into p, right? So let's say uh, their representation in base p is, let's say, n naught, n1, n2. These are all digits in base p. Let's say it has k digits in base p n, and r also we will have in base p. We'll assume uh, its representation as r naught, r1, r2, and till rk. So Lucas theorem says that NCR mod p is just simply equal to product NICRI mod p. So we go on individual digits. We go n naught CR naught into n1 CR1 into n2 CR2. We multiply these all and uh, calculate their NCR mod p them and product them all. This will give us NCR mod p. And if any time Ni is less than Ri, then we say NICRI is 0. Okay, so that's all what Lucas theorem says. I'll not very much go into details. It also has many applications, but honestly saying, generally those are the cases where P equals to 2 is main use case. Uh, this is that's it from my side on teaching part. I'll just go with the problem, give the solution of it, and then just end the session. So here is a problem, lost array. I'll share the link in YouTube only with that wherever. Yeah, so I've shared the link in the YouTube stream. So the problem states that initially you are given an array, you convert it into a matrix such that initially array B was given, you converted it into a matrix. Sorry, initially A was given. Now B, the first column of B is all zeros. The first row of B is all AIs, and we have this relation like the matrix is just the XOR of the left one and the upper element. So now initially the matrix was of n cross n, and now they have just given you the last column and they are asking for the first row initial array. I think the problem is pretty clear. Let me give you a visualization. So initially there was an array A. Let's call it A naught. Right. Yeah. So initially, let's say it was A naught, A1, until it was given till AN. Now it was a simple array. We converted everything into a matrix B, which has the first column as zeros. Okay, I think that's visible. Mark these all first columns as zeros. And now this element is just the XOR of this and this. Oh, oh, right, right. My bad, my bad. Yep. It's going to लिख देते हैं. A1. Yeah. So this is the first row of B, right? This. And if now the matrix would be something like this, if we want to create. This would come something like A1 or A2. And this element would be the XOR of all elements, right? A1 XOR A2, dot, 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 dot. Right. This is now this element would be just simply A2, and the relations become complicated. Like so, the end result is given. This is given, and we have to find this, or we have to tell it's just not possible to have an animation. That will never be the case. But yeah, so given the last column, we have to find the first row. This element is the first column. Yeah. I think or just this is given. I think till n plus one it is given, and then we have to find till this. I don't know. Let me see the problem for this. Like, yeah. Must be, however, many elements of the matrix are not the only know the values of VIN. Okay. Yeah, that's all. Okay. Okay. Yeah. So this is given, and you have to find this. So the first element will be the XOR of all elements. The second element would be something. The third element would be something, and so on. So how would you go on? Should I give time or should I just start telling the solution? Okay, let's start on that. So if we view this column wise, if, yeah, if we view this column wise, the first, this is not the first column. This column, everything would be A1. In this column, A1s or A2 will get alternated, right? And so if we clearly observe, it's so I just want to know that uh, let's say some element here, which of the following will be present, for example, right? So for that, if you note closely that uh, is or this, like for example, this contributes to this contributes to this contributes to this and this, and so on, right? So if I want, let's say, an A2 in my expression, then my claim is that the number of paths from here, let's say, because there is no path from here, like these are the first rolling count. So the number of paths from here to here, if this is an odd, if these are odd, then we would then A2 will contribute to this, else A2 won't. Like in here, if the number of paths from here, because first step is always downward only. So the only steps allowed are right and down, right? So the number of paths from the starting point to the ending point, if those are odd, then the starting point will contribute, else it won't. Okay. So in these scenarios, what is actually the number of paths? Right. So for an, the number of paths is always one for each. Every element is this column. So we know for sure that a1 will be present in each of them. Right. For an minus 1, an minus 1 will be present in this one. So will be present here. N minus 1 will be present in this one. So an minus 1 is present in this one and this one all. So an minus 1 won't be present in this one, right? The an2. Yeah, this is sorry, this is bn0, this is bn1, this is bn2. So in bn2, we know that an minus 1 would not be contributing. So if we somehow know for each element which of them would be contributing and which of them would not be, then we could do something, right? So for doing that, to calculate the number of paths, so I let's say first I will reverse the indexing because it's easier to look at, honestly. Sorry, I'll do this A1, honestly, A2, and mark this as AN and these are all as 0, right? So I say A1 is present in all of these and the number of paths, let's say this is BN1, right? So my problem I need to solve right now is in BNI, what's the does AJ contribute? Right. So to do that, we need to find the number of paths from AJ to BI, right? So for A1, we know it's one for each. For A2, it's so how many we know that there are I minus one down steps possible and J minus one right steps possible, right? Because from A2 there is one right step possible and to reach B and I minus one down steps are possible because we start from here only, right? So the number of ways is simply I minus one plus J minus one C I minus one. This is a pretty well-known combinatorial result. I don't think I need to explain this. So, right. So if this is odd, let's say, I'll do this zero-based indexing again. So this is already written. So basically, if I plus j c क्या हाँ हाँ वो ठीक है वो डिराइव कर लेना हाँ तो if this is odd then contribution आएगा वरना नहीं आएगा right. So to check whether this is odd or not, we need to check its mod too. So I plus j, I plus j, cj mod 2. कहाँ है वही देख रहा हूँ. Wait a sec. Yeah, this line ना. हाँ तो हाँ ठीक है ना. Yeah, so this is the quantity we want to calculate, right? तो अब हर आई प्लस जे और जे के पेयर के लिए निकालने बैठेंगे तो ऑफ कोर्स वी डोंट हैव दैट मच. n काफी, n is quite large, so we can't do that. So for calculating this we need Lucas theorem. So what Lucas theorem states that if we represent I plus j in base 2, let's say this would be some digits d d0 d1 d2 dot dot dot, and if we represent j, this would be, let's say, j1 j2 dot 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 dot, right? So now what we need is that this quantity, uh, NCR of this should be odd. So for this being odd, we know that any of these digits, as we know, D naught, all DI and JI are either 0 or 1, right? Because we have converted them into base 2. So we know that for this to be odd, we know that every NCR should return 1. If any of these is 0, then the product would be 0. Right. So we can have, when can we have 1? We can have 1 on 0C0, we can have 1 on 1C0, and we can have 1 on 1C1. 0C1 gives 0. Right. So we know none of the pairs, if it contributes, none of the pairs should be, the upper digit should be 0 and the lower digit should be 1. So what we are basically claiming is for J to contribute in, sorry, uh, was J, one second, let me scroll up. Okay. I was calculating the contribution of AI in BJ, BJ in AI. Yeah, so AJ, BI and AJ, right? In BI does AJ contribute? Right. Yeah. So we know that we don't have a 0C1 pair if the contribution is happening, which means that J is submask of I plus J. Right. Which further means that I and J is 0. Because if I and J is not 0, like we know that I plus J has all entries 1 wherever J is 1. So if we do I plus J minus J, so all the entries that J has 0 should only be left 1. So we can say that I and J is 0. Right. Yeah. So B, and I forgot what the hell is happening with me. Okay. So what was I calculating? AI contribution, BI, does AJ contribute in BI, right? Yeah. Yeah. So for that to happen, I and J should be 0. This is the condition. Uh, Now to have this, we can further apply some of subset dp to calculate this and have at it. For further explanation, I'll read the editorial. Actually, that's more explanatory. That's what it is saying. N minus I plus j minus 1, cj minus 1 is odd, else 0 otherwise, right? So, first it tries to solve the reverse problem. Given array A tries to construct B. By Lucas theorem, this should be 0, which means n minus I is a submask of j minus 1. I just reverted them to this, right? It just calculates the data transform and then calculates the Mobius transform after it, and the final solution just ends there. So mainly, the problem could be happening to the tutorial in detail. Again, the details would take much more time. So basically, what I wanted to show was the application of Lucas theorem. Like the initial problem was simply making a matrix and drawing, but this condition came out with the help of Lucas theorem, and it is a major help in the final solution. I just wanted to share some usage. Yeah, yeah, that's all from my side. I think yeah, that's all. Yeah, Vedant, I think we can end here. Yeah. Vedant, are you there, Vedant? हाँ हाँ आई गेस हो गया एंड लास्ट 2 मिनट से दिख रहा है स्क्रीन पे कुछ आ ही नहीं रहा लास्ट 2 मिनट से ब्लैक स्क्रीन आ रहा है यूट्यूब पर आई होप सो आई होप सो आवाज नहीं होगी तो फाइन ओनली एडिटोरियल था मैं तो बस यूज केस बता रहा था हाँ इसलिए बहुत एग्जैक्ट डिटेल्स आपको पूरी ना प्रॉब्लम की आई जस्ट रिमेंबर्ड कि इट्स अ गुड वन सॉल्व भी कर रखी है मैंने भूल चुका हूँ हाँ आवाज तो आ ही रही होगी मैंने बहुत ज्यादा लिखा तो नहीं है 60 seconds but still the last screen was something like this मतलब मेनली ल्यूकास थ्योरम का एप्लीकेशन ही दिखाना था मुझे Nothing much, I think. ठीक है बंद कर दो मैं हाँ अरे नहीं मतलब मैं ल्यूकास थ्योरम का एप्लीकेशन नहीं बता रहा हूँ और क्या 0 से 0 भी काउंट करना 0 से 1 ये या वो तो ठीक है तो बेसिकली द डिजिट्स that we need to count so for them to be odd all of them all of the multiplication needs to be of this kind only. So 0 C1 shouldn't occur, which means that I plus j should be a supermask There should be a submask of I plus j, which further translates to I and j should be. And if I and j is zero, then only it will contribute. And then further, the problem has some Mobius and Wiener transformations that, like, the Mobius transformation for mine needs a different same topic, but if I go and teach that, it would take a lot of time. The tutorial is present here only. So. Yeah, I think we can stop there. And एक बार स्ट्रीम ऑफ करके बात करनी है actually.